So this is the outer mitochondrial membrane here. Then we have the inner mitochondrial membrane here. And then consequently, the space between is called the intermembrane space. The intermembrane space, okay? And that would be the space in between these two membranes here. Right, the most, or the space inside the inner mitochondrial membrane is called the mitochondrial matrix. Right? And what we're going to be looking at is a series of proteins and complexes that are embedded in the inner mitochondrial membrane. We're going to talk about 4 of them. Okay, let's just call these complex 1, complex 3, complex 4, and this one is called ATP synthase. Okay. All right, so let's remind ourselves of those electrons that we gathered through glycolysis, through that linking step, and through the Krebs cycle. All right, we brought all of those reduced molecules, which were NADH+, right, NADH plus, and FADH2. And we're basically going to oxidize these back to their oxidized form. So this will be NAD plus and FAD. And so what we're doing now is taking those electrons, right? We took those electrons off. This is an oxidation here. We're going to take these electrons that we shuttled into the mitochondria, and they're going to be passed through this first complex here. Okay, they're going to go through complex 1. Now there is a complex 2. We're not going to talk about complex 2. For the sake of simplicity, your book leaves it out. But complex 2 specifically deals with FAD2 electrons. So the electrons that are coming from FAD2, but don't get too bogged down in that. So from complex 1 to complex 3 here, then from complex 3 to complex 4, and then they're going to come out from complex 4 and they're going to be donated onto this oxygen. Okay, this is the whole reason that we need oxygen. Oxygen acts as the final electron acceptor in this electron transport chain. Okay, let's just draw that out here a little bit. So we have these electrons, right? So these electrons that we shuttled across plus protons are going to yield, plus this oxygen that's sitting here is going to yield us H2O. Right? So all this gets turned into water, which is how this oxygen accepts those final electrons. Okay. Now this part of the process is only the first part. This is only to facilitate the second part of what's going on here. So the second part of this is that we have protons, right? So there are a few protons in the mitochondrial matrix. And then there's a lot of protons, so there's a high proton concentration in the intermembrane space here. Okay. Right, so we have a low hydrogen concentration. And hydrogen is what I'm calling protons. Those terms are synonymous. There's a decreased hydrogen concentration in the matrix, and then there's a high hydrogen concentration in the intermembrane space, okay? And so each time an electron moves from one complex to the other, we basically generate some energy that can pump a proton across this inner mitochondrial membrane, okay? And again, this electron goes from this complex to this complex. Again, we harness that energy to pump a proton across the mitochondrial membrane. right? And we continue to do that all the while moving protons from their area of low concentration to their area of high concentration. And because this is going against the concentration gradient, this requires energy. That's why we need the movement of these electrons across this chain, okay? And now, the purpose of oxygen here, just to go back into this a little bit, oxygen must accept these electrons, otherwise this entire process backs up. This is why we breathe in oxygen. This is the sole reason that we breathe. Oxygen sits in this mitochondrial matrix and takes those electrons to keep this chain flowing so that we can continue to make this concentration gradient with protons. All right, let's talk about what the concentration gradient does now. Now that we've created this concentration gradient, and just to talk about that a little bit more, I simply mean that there's more protons here than there are here. Now we have a natural phenomenon where these protons want to flow down this final complex here. Okay, and as they flow down this final complex, this complex is called ATP synthase. This is the area, this is the step where we're going to phosphorylate ADP. Okay, so I kind of messed this up. So this should not be pointing to H2O, so I'm just going to move this here, right? This is basically the phosphorylation of ADP to ATP, okay? Let's explain that again, right? So you're not going to get this the first time you see it, so we're probably going to have to go over this a couple of times, unless you've been exposed to this topic already. So basically, the electron transport chain is these series of complexes. We're passing electrons from one complex to the other complex to the other. And as we move these electrons across this chain, we're pumping protons against their concentration gradient. So they're being pumped from an area of low concentration in the matrix to high concentration in the intermembrane space. Eventually, we build up a gradient where there's more protons out here than there are in the matrix. And so naturally, the protons are going to flow down their concentration gradient through ATP synthase, and in doing so, we phosphorylate ATP here. Okay, now we yield a lot more ATP through this process. This is a very efficient process of generating ATP. We generate roughly 28 ATP per single molecule of glucose that we break down. And when I say per single molecule of glucose, I mean the fact that breaking down glucose is yielding us the carriers, yielding us the electrons that we needed. Remember, we got these electrons from glycolysis, from the linking step, from the Krebs cycle. And so breaking those down yields us the electrons to sort of make this machinery work, to create that gradient, to then create ATP.